now let us look more closely at homogeneous equations with constant coefficients. Right? So here is the simplest example, the harmonic oscillator. Let's just try to guess the answer. So let us try to substitute if y is e of t, right? So then if, sorry, e to the t, right? So if y equals, sorry, e to the t, then y prime equals e to the t, y double prime equals still e to the t, and then of course y minus y prime double prime equals e to the t minus e to the t, which is 0. So this function does satisfy the differential equation. But in the exactly the same way, if we try y e to the negative t, then y prime is going to be minus e to the minus t, and y double prime is going to be e to the minus t again, and then of course y minus y double prime is going to be e to the minus t minus e to the minus t is 0. So this function again satisfies the differential equation. But then if you try e to the minus t or the sum e to the t plus e to the minus t, it's still going to satisfy the differential equation. And I think you can guess that anything of the form that is a linear combination of e to the t and e to the minus t is still going to be a solution of this differential equation. The intuition here is that since there are two parameters here, then probably, and the differential equation is second order, then it means that probably we have found all the solutions. So generally speaking, a second order differential equation must have a two-parametric family of solutions. But of course we need to develop some theory to be able to prove it rigorously. So later we are going to see why that this is true, why that there is nothing else but this. So let's look at a more complicated example. So just by the analogy with first order linear differential equations and our simplest example of a second order differential equation, so let us try some kind of exponential functions as a solution. Right, so let's just write it in the more general form. So let us write that y equals e to the power rt, where r is the unknown parameter. Right, so then we can calculate y prime and we can calculate y double prime, and then we can substitute this into the original differential equation. Right, so what we did here is we just take the expression for y double prime and plug it in as y double prime here, then we plug it in here and plug it in as y. So that's what we did. Then notice that the equation is this. Sorry about that. Right, so this must be equal to 0, since e to the rt can never be equal to 0. So in other words, what we just saw is that such a exponential function is a solution of the original differential equation if and only if the constant r is a solution of the usual algebraic equation that you learned in primary school, just the quadratic equation. And I hope you know how to still remember how to solve this. So there are just two answers. R is either 3 or -8. So let me emphasize it again that these two numbers, 3 and -8, they are solutions of this algebraic equation. But because of the same kind of reasoning that we saw in the previous example, anything that is a linear combination of these two is going to still be a solution of the second order differential equation. Alright, so the general definition. So if you have a second order homogeneous linear ordinary differential equation with constant coefficients, then if you just replace y double prime with r square, y prime with r, and y with 1, which is r to the 0 in a way. So let me write it down. So we kind of replace y double prime with r square, y prime you replace with r, and y you replace with 1, which is r to the 0. Then you get an algebraic equation, and this algebraic equation is called the characteristic equation of the original differential equation. So, I mean, of course we only did it in a specific case, but you imagine that it's going to work in all other cases too. So it's just, if you change the specific coefficients like 1, 5, and 24 was it? I don't remember. With A, B, and C, then the same thing is going to work. But the important part is that if R is a solution of the characteristic equation, then the function e to the RT is going to be a solution of the corresponding differential equation. And then another thing that that we know is that a quadratic equation usually has two roots. Not always, and sometimes these roots are complex, but there are two roots, and if the roots are real, then we have this. Alright, so a few questions that we still haven't solved. First, how do we know that this formula covers all set solutions of the differential equation? So what do we do if the characteristic equation has a repeated root or complex roots? Then what if the original differential equation is not homogeneous? And finally, what happens if the coefficients of the differential equation are not constant but rather some functions of t? And the funny thing is that although questions 1 to 3 seem easier, and they are easier, but as often happens in mathematics, it makes more sense to try to solve the harder question and develop a general theory, and that general theory happens to successfully answer easier questions 1 to 3. So we are going to, in today's lecture, we are going to introduce a general theory that is supposed to, to answer the fourth question, but instead we are going to, at least today, we are going to fully answer question 1, and later we are going to fully answer questions 2 and 3.